We could have
Um,
scheduled meetings.
yeah. Let's see how to say it. Right. So you know how people think about relativity, if you just sort of first talk to somebody about relativity and
Hmm.
the things that you hear about it are like how strange it is, how counterintuitive, right? That
Hmm. Hmm.
space and time shouldn't work this way. This is so
Hmm.
bizarre that space, how can time be different for different observers and stuff like that, right?
Hmm.
And yet, if you back up and you say, here are two principles about how the world might be that seem perfectly intuitive and perfectly reasonable to
Hmm.
almost anybody. One is
Hmm.
that the reality is sort of unbiased with respect to observers, right? That it shouldn't kind of, that's what the
Hmm.
principle of relativity actually is, right? Is that
Hmm.
it's a sort of a simplest default assumption that you would kind of make is that, well, one observer's point of view shouldn't be preferenced over another observer's point of view. There's no
Yeah.
reason for them to be different. So that's perfectly common sense. And then the idea that if you really, I mean, actually, this is sort of related to our thinking about can we derive physics from kind of what's necessary in order to just make
Hmm.
everything consistent in a
That's
reasonable way.
yeah.
And and actually, if you think about it a little bit, this is what I was kind of meditating on, is that I think it actually is almost a given that there should be a maximum speed at which you can travel relative to other reference frames. Because
Hmm.
because if there weren't, it would lose space would almost lose its
Mm.
meaning as, in some sense, the role that space plays in our experience with
Hmm.
the world is that it keeps everything separate in some way, right? It makes it
Yeah.
possible for one observer to be kind of different from another observer. That's almost, we talked about the filing system, right? It's
Yeah.
almost what space is. And if there were no limit to how fast you could move through your own coordinate system of space, then it almost ceases to have meaning that two places are different. If you can instantaneously move between two places, then they
Mm.
lose their their role of being different. You know
Yeah.
what I mean? If you could
Yeah,
literally
like
travel
space
infinitely
just
fast,
like isn't
it,
a thing.
yeah, exactly. Like I think we've talked before about, I mean, lots of people talk about this in different ways, but John Wheeler had a famous line where he said, time is what keeps everything from happening at once, and
Hmm.
space is what keeps everything
Space.
from happening to me.
Yeah.
And
Yeah.
and so in those terms, if you want to use his language, in those terms, if it was possible to travel at arbitrarily fast speed within your reference frame, then space wouldn't keep everything from happening to you because everything would be
Hmm.
accessible,
Hmm.
right? You know what I mean? Like you wouldn't be safe from
Hmm.
something. We can say, well, whatever
Yeah.
happens across the galaxy right now, it's not going to directly influence
Yeah.
us. We're protected, right? If there's evil aliens out there that want to dominate the galaxy, at least it's going to take time for them to get to us, so we're protected.
Hmm.
But
Hmm.
that protection would be gone if it were possible to travel infinitely fast,
Just
right?
instantaneously.
Yeah. So,
Wow.
so my point is just that those two statements are actually very reasonable. I mean, I think if you just asked a person on
Hmm.
the street, like, does this seem reasonable that the universe would work that way? Nobody would say, "Oh, wow, that's really surprising and that's really weird." Like,
Yeah.
how could that be that the universe doesn't have a bias toward one observer or another? Or how can it
Hmm.
be that there's a fastest speed that things can travel around? I don't think most people would think that was weird.
Yeah. It's funny, like it makes me think of kind of the same vibes of like, why is the universe just right for life? But like the speed of light being like 3 × 10⁸ like if it were any faster, like would this inconsistency of having space and time be separated become an issue, or like if it was like slower than 3 × 10⁸ like would like the value that the speed of light is, like if it was altered, would that disrupt the filing cabinet of space and time
Y-
that we
Yeah,
currently
yeah,
experience?
yeah. That's a good question. I mean, I think, if you back up to think about the fact that our our existence and the units that we use are all scaled from what the speed is. You know what I mean?
Mm-hmm.
Like
Mm-hmm.
if the speed of light were numerically faster or slower, then probably our scale that we operate on would be
Yeah.
correspondingly different.
Yeah.
You know what I mean? Like it's
Yeah.
like our units are pegged to the speed of
Mm-hmm.
light. Like, yeah.
Right. So it's kind of like potential energy where we can kind of just like choose an arbitrary like
Hmm.
zero. And then if it gets like shifted, then we just need to shift our meter sticks and clocks.
Right. I mean,
Uh,
right. Except that in this case, our meter sticks and clocks are actually expressed in terms of the speed of light, right? I mean, it's like
right, with C. Yeah.
like in like a meter doesn't really have a fundamental meaning, whereas the speed
Mm-hmm.
of light does.
Mm-hmm.
And the meter is sort of
Yeah.
derived from that, in a way.
Mm-hmm. Because it's like the mass of an electron or like one of those like fundamental or not mass charge for an electron,
Yeah, right, right, right,
like fundamental constant.
right. It's like the dimensional, like the Planck scale, right? I
Mm-hmm.
mean,
Mm-hmm.
if you take C, G, and H bar, you can build natural units out of those that have like some kind of real meaning to them.
Right, right.
Unlike, a furlong or a meter
Mm-hmm.
or whatever, or
A
a month
fortnight.
or a fortnight, right? Those,
Or a stone. What was it?
yes, yes. The Planck mass in stone.
Mm-hmm. Mm-hmm.
Yeah. Anyway, so the reason I was bringing all that up is, right, you have these two sort of very natural properties of the world that I think people wouldn't think are weird.
Mm-hmm.
And yet, if you grant those two properties, then space and time have to be interchangeable,
Mm-hmm.
right? Once
Mm-hmm.
once you've agreed that there's going to be a maximum speed, and you've agreed that you're not going to be able to tell which reference frame is special,
Mm-hmm.
then because I mean ultimately it's just because speed is velocity, or sorry, velocity is distance over
It's
time. And
right.
so if you're going to have, if you start having one
Constant
observer
B.
moving relative to another, then, this event and this event are in the same place for me and separated by some amount of time. If I have a reference frame that's moving relative to that, then they're going to be a different distance. They're not
Mm-hmm.
going to be in the same place. There's going to be some non-zero distance. And so if I'm going to have a maximum speed that's going to be the same as measured by everybody, the only way you can do that, given that people will disagree about where those events occurred, the only way to make a speed be the same when a distance is longer is to make the time be longer,
Yeah.
right? I mean,
Mm-hmm.
basically a fixed speed with different distances requires time to be different. And so then
Yeah.
all the things about relativity were basically, if you keep trying to go faster, what basically happens is you can make so like if I'm the proper observer where things happen in the same place, and I do snap,
Mm-hmm.
and then 1 second later another snap. If you're moving relative to me and you see snap, and then sorry, I just do it in one dimension with snap, and then 1 second later you see snap, and they're separated by some amount of distance, right? Um, if in order to keep the ratio of distance over time the same, you have to have your time for those two events seem longer in order to make it all work out, right?
Mm-hmm.
So in some sense, I'm just really surprised that it took so long to discover relativity. Not only is it not
Yeah.
strange, but it's sort of necessary
Mm-hmm.
for any sort of simple way of viewing the world. And I wonder I think quantum mechanics could probably be expressed that way too, right? If you just back to
Mm-hmm.
what are the core principles that have to be in place in order for maybe, like you said, maybe for to be just right for observers, or maybe even more general than that, maybe just to make it logically consistent. What
Mm-hmm.
has to be in place? All the supposedly weird things kind of become logical consequences of these very natural principles, which I think is really interesting.
Yeah.
Anyway, so it's worth
No, I
my
like that.
ultimate point is it's worth meditating on that science thing.
Mm-hmm. Yeah, very much so. Like, I don't know, just even taking like one natural um solid assumption and then just seeing what happens.
Yes, and deriving the consequences. And I mean, a good
Mm-hmm.
starting point is just to start with the one that led to special relativity, right? It just,
Mm-hmm.
remember drawing out the triangles and seeing, okay, well, this is the hypotenuse and this is one leg of the
Mm-hmm.
triangle, and we've insisted that these are the same two events seen from two perspectives. One of them sees it as this segment, one of it sees it as this segment. And
Mm-hmm.
so you derive the Lorentz transformation from
I
that.
don't
But
remember doing that.
well, we should do it then.
Yeah,
If
I
you
think
if
that would be good.
Yeah, actually that's a really good exercise to do, right? If you let me if you want to, should I get my tablet?
Oh yeah, yes, please. That would be good.
Not forcing this on you, but
I
this could
won't.
be a good practice for what you were talking about in your um,
Therapy
therapy
session.
session about the uh, when is it fun,
Meditation.
right?
Yeah,
Basically, when is it fun to think about deep things and just seeing how that works. Let's see. Why? Here we go. I'll just add it to our existing document here. Um, let me grab my notes because I have something where I did it the other day. Then we go.
I see it.
All right. So let's see. right? So the the way that I've usually seen it or thought about it is if I have two observers, so I'm going to make I'm going to do this. Okay, so I'm going to make one observer. Um, oops, my pen back. There we go. So I'm going to have one observer like this is their coordinate. So this is going to be I'll call this the observer 0
Hmm.
because they're going to be the proper one. Okay, and they are
Okay.
so this is uh, think about how I want to do this. Well, it's probably better if I just make it up on the fly and then I'll correct. Then we
Yeah,
stay connected to the intuition and then I'll correct if need be.
exactly.
So the idea is going to be that this reference frame is moving at some velocity v
Hmm.
relative to another reference frame, all right? And this reference frame I will draw in blue and I hope it'll make a straight line for me. Yeah.
Wait, the proper one is the one that's
The proper one is where everything happens in the same place,
okay.
where there's
Okay.
no spatial separation in your coordinate system, right?
Yeah.
So this observer O, and this one's going to be I'm going to call this one observer, observer one, and the idea that observers observer zero is moving with a velocity v as measured by observer one, right?
Hmm. Okay.
And of course,
Yeah.
it's symmetrical according to the principle of relativity. So you could equally well say that observer, this one, observer zero, would see this other reference frame moving at
That's the
velocity
other
v in the other direction, right? Minus v.
one. Hmm.
Yeah.
Hmm.
So this is going to be like, um, I guess the coordinates here, this would be like y1 is in this direction, and I'm not sure we're going to need this, but I'll call this x1 in this direction, and this would be, um, you know, y0 and x0, right?
Yeah.
And in fact, I guess I might as well, for simplicity, um, because there's no motion in that direction, uh, y1 and y0 are going to be the same. Does that make sense?
Hmm.
Because there's nothing to make anything
It's
different,
just
and
going this
they're
way.
just, yeah. And from a sort of the way I often think about it is you could leave a permanent mark. You could, as these reference
Hmm.
frames go by, if this guy had a paintbrush, they could leave a mark there and you would see whether they lined up or not. And there's no
Hmm.
way of changing that because
Hmm.
they're at the same place in that direction. But you can't do that in this direction because they're continuously moving, and so you can't pin things
Yeah.
down. Yeah.
Yeah.
Okay. So then the idea is that um, observer zero, the proper observer, has is carrying with them a light clock that has, essentially, I'll draw it in temporary first, and then we'll um, make it green, and then we'll make it permanent. Right. So the idea is this observer in their own frame has a source of pulses of light down here that travel upward, hit a
Hmm.
mirror up here somewhere that
Hmm.
bounces them back, and they travel back down, and the back and forth of that is a clock. right? It's
Right.
just it'd be like literally me holding two things here and I'm watching, you know, a light pulse go up and down. And every time it
Hmm.
does that, I could make that like a tick of my clock, right? I could make that a time.
Right.
Okay.
Hmm.
So if we then define a time t zero between these two events, which I could draw as like, here's the bottom one and here's the top one. And I could call this event one and this is event two is, when the light leaves there is event one and when it arrives here is event two. Okay.
Hmm.
And so, and it's going to be light. So the speed of light is c.
Yeah.
So that means this distance
Just CT.
is going to be c times what I'm going to call t zero.
Hmm.
Yeah. Which is just the time as observed by the frame in which
In,
these things are in the same x coordinate,
right.
right? That happens.
Hmm.
Okay.
Which is right on top of each other
Which is
instead
right on top of
of
each other,
them.
right? So it's boring in a sense, right?
Yeah.
I'm staying right here. And I'm just watching this go up and down.
Hmm.
Okay, but now if I want to ask about that same, you know, so guess I could do it like this. We can actually do it. I'm doing it here.
Uh-huh.
It goes like this, but I'm with respect to me, my clock is not moving, but with respect to
Hmm.
you, I start one place and I go over here. I
Hmm.
move past at some constant speed v, right?
Hmm. So then it starts going like at a diagonal.
Exactly. So in your reference frame, so now if I do, I have to, it'd be hard to do this on the same drawing, so I'll do it in a separate, scene from O1 perspective. Sorry, I didn't O1 perspective. And it's the same. This is key. This is hard to keep track of sometimes. It's the same two events,
Hmm.
right? It's actually light leaving the bottom mirror and light arriving at the top mirror. It's still the same
Hmm.
events. It's just as seen from a different reference frame, right?
Hmm.
So then, as
I
you
think
just said, what's
Brian
that?
Green, I think Brian Green like used, I don't think he like derived the Lorentz transformations from this, but he talked about like conceptually like this mirror idea and then
Yes,
having it move and having the distance be longer because the hypotenuse of the triangle when it's moving you have a longer distance because up and down is going to be like for like a triangle like if you draw a triangle the
right.
leg of the triangle is going to be a shorter distance than the hypotenuse of the
Exactly.
triangle so the
Exactly.
distance is going to be larger.
Right.
um
That's the universal. I mean, everybody uses it, right? It's the famous light
mhm,
clock experiment. Right. Exactly. Right.
mhm,
Right. So yeah,
mhm.
it's in Brian's videos and it's in all the textbooks. And yeah, I mean, it's like it's the
The classic.
it is the essence of special relativity. Exactly. Right. Yep. So, right. And remember, so and it doesn't even it's I think it's important because people tend to not emphasize this. It
Mhm,
doesn't have to be light. Like that's why the way I was saying it, I was sort of careful about just saying a maximum speed, right?
mhm,
So C is is the maximum speed. It doesn't really, in fact, it's not really the speed of light. It just happens that light goes at the maximum speed.
mhm.
right? But
Hmm.
it's not anything special. Well,
Yeah, true.
sort of special about light, but I mean, gravitational waves also do this, or maybe there are other,
Right.
it's just
The
the sh-
things that don't have the mass that weighs them
well, right. So
down to,
there's a whole mass issue that comes in, right? But for now, I think we can just say, I think it's simplest conceptually to just say that it's just you're going to say that there's a maximum speed that uh, anything can move as seen by any
hmm
observer in their reference frame.
hmm
And it will turn out that only things that don't have an invariant mass can go at that speed. But for now, we don't really even need that. But I mean, you're right. Okay, so then, yeah, I mean, you basically just outlined the argument, right? I mean, it's that, but I just want to highlight some things to make sure they really
yeah,
pop out, right? Is the fact that so from this perspective, I'll just sketch it. From this observer's perspective, it has to be the case because of the fact that the clock was moving. It has to be the case that event one happened here and event two happened somewhere over here, right?
hmm
Because that's what it means for it to have a velocity, the reference frame to have a velocity. I mean,
yeah,
velocity means distance over time. So if any time went by, the clock had to move relative to this observer's reference frame,
hmm
right? So we don't know
hmm
how big this dis well, I mean we can calculate it, I guess. Um, this distance has to be
delta x squared plus
well, it has to
t.
be the how far this is. This is
Hmm
basically x. You're right. It's like delta x1,
hmm
and that's got to be equal to v
v hmm
times um, you know, in fact, I'm going to lose the deltas just because we don't, the x's are going to be the intervals, okay, just so we don't have extra
Okay.
symbols. Right? So
hmm
x1 is this distance, and it's equal to v times t1,
hmm
right? And I had, if I didn't know what I was going with this, I would feel strange about using t1 because I'd assume it was the same as t0, but I do have to be careful and use t1 because I'm doing it in the O1
Right.
frame,
In the
right?
frame of one.
So however much time went by for me in the O1 frame, multiplied by whatever the velocity is, relative velocity between the two frames, that has to be how
hmm
far this has moved to the right,
hmm
right? And then we're assuming that, so I can go ahead and, you know, make that a triangle. Oops. I can go ahead and make that a triangle and actually draw that in there as that length. So we'll just label it VT1. And then this is got to be the same height as the other in the other frame, right? Because we're not moving in
Doesn't
that direction,
change.
so there's no relative motion. So I
Hmm
can say that that distance is CT0,
hmm
right? Because I already have a name for it.
Interesting.
Okay, and then and then here's where because so now this is what you were saying about the Pythagorean theorem, right? If
Hmm
I want to know what is this distance, um, I have a name for it because I've said that the speed, and I mean now I am talking about light because it was a light pulse. So I've
Hmm.
said that the light has to travel through my frame at a speed c, which is the same
Hmm.
c as this one. And
Yeah.
so this is where we back ourselves into a logical corner, right? This has to be CT1,
Hmm. But
right? Yeah, think about that because that's maybe not obvious. From my point of view, the light did this.
hmm.
So it traveled whatever that distance is at this speed for some
Hmm.
unknown amount of time in my reference frame. And I can represent the distance that it covered, right? So D
Right. Yeah.
is however fast it went times however long it had,
Hmm.
right?
Yeah. I think it's just now it's like two-dimensional with
Hmm.
X and Y components.
Hmm.
But I guess that doesn't matter. It's still traveling at that velocity for a certain amount of time, so it's going to go a certain amount of distance.
Yes. And it
Okay.
is worth thinking slowly and carefully and appreciating the stuckness there.
Hmm.
Because
Hmm.
really, once I just made that statement and said, right? And trying to get you to
Hmm.
agree with me. Once you agree with me, everything's done. Like, I mean, I think it's really worth thinking that through. Everything else is just algebra.
Hmm.
As soon as you agree to let me write that down, we're done. Everything else is going to be algebra. So the place
Hmm.
to argue about what reality should be is all buried in that. So you're right to be
Because I think
scratching at me.
also like if the path, like I think the thing that my brain is freaking out about is like I guess if you were in the O1 reference frame
Uh-huh.
and the path was instead like it traveled a speed v for a certain amount of time t vertically,
Uh-huh.
I guess then that distance would be the same distance as if the path was like this, traveled at a speed c. Yeah,
Right. Because
I'm
if you were
convinced.
in the bottom reference frame and it went straight up, then you'd be the proper observer.
Hmm.
And it would be different, it would be two different events,
Yeah. Hmm.
which I think is what you're saying, but I'm just
Yeah.
reinforcing it.
Yeah.
So this is where the weirdness is, right? It's like from one point of view, there's some light that just went like this from
Hmm.
here to here. The part, at least for me, is takes a while to fully wrap your intuition around, is that those same two events, light left here and light left here, seen from a different point of view of somebody with respect to whom this is moving, light left here, light doesn't go straight up, light goes this way,
Hmm.
right? So the same
Hmm.
two events have a different path through your space-time filing system is a different coordinate system than my space-time filing
Right. Yeah, because the
for the same
distance,
two events.
the D that's circled right now is D1,
Correct.
which is different from the distance in the O0 proper
You're
frame,
absolutely
which
right.
is D0. Got it. Okay.
Good. Yep.
That was the thing that was tripping
So in fact, let's recap it conceptually. If you were trying to teach this to someone, Riley or whoever,
me.
right? Or a student. So the key thing is that D1 is definitely bigger than D0.
Hmm.
That's the anchor. Actually, there are two anchors. D1 is bigger than D0, and yet also we've insisted that C, uh, C1 equals C0 equals just C.
Hmm.
But is um, C1 is by definition uh, D1 over T1,
Hmm.
and C0 by
Interesting.
definition, right, is D0 over T0.
Hmm.
So let's write this out again. So that means that D1 over T1 has to equal D0 over T0. But
Which
we also said that D1 is
D1
bigger than
is
D0.
D0.
Rewrite that here, just in the top part. D1 is bigger than D0. So that
Hmm.
means the only way that this is going to work is if T1 is bigger than T0.
Hmm.
That's like, so that's why I said as soon as you let me write this and this, everything else is algebra because now I've made it so that T1 has to be bigger than T0. And then I'm just doing Pythagorean
Hmm.
theorem to figure out
Hmm.
the transformation rule. But conceptually, you don't, if you're trying to explain it to somebody, you don't need to bother them with that derivation. You just need to
Yeah.
show them, well, you agree with me that this is farther than that this. If you agree with me that this is farther than this,
Hmm.
and if you agree that I can represent this as C times T1, and if you agree that I can represent this as C times T0, then the C's cancel, and
Hmm.
you've just admitted that T1 is bigger than T0.
Hmm.
You don't have any other choice.
It's so funny. Like, if I don't know, like if there was just like some question that was like, if C1 equals C0 equals C, what does that say about D1 over T1 and D0 over
Mhm.
T0?
Mhm.
Without knowing that D1
Without
is greater
knowing
than
what you're
D0,
describing. Yeah, right.
yeah, if you don't know that, then you're going to be like, oh, well, D1 over T1 just equals D0 over T0, but that's not the case. Like, that doesn't necessarily, like, because ratios can be different and equal the same value.
That's
But I
right.
don't know why it's so natural for me to be like, oh, just D1 over T1 is equal to D0, or D1 is equal to D0 and T1 is equal to T0.
Yes.
But there is, this is a case where that's not true, and
Right.
the C's are the same, but the um, numerators and denominators are different.
Right. I mean, it would almost be useful as kind of like if you, again, if you were teaching this at a, high school or conceptual sort of level or something. It
Hmm.
again, like you said, if you don't even think about relativity, if I let's say I told you you had a car that you could hop in and its speed was locked at 60 miles an hour.
Hmm.
Like this car just you turn it on and it's going 60 miles an hour. There's no other choice.
Hmm.
And then if you ask how long does it take in this car to go 60 miles.
Hmm.
And then how long does it take in this car to go 120 miles?
Hmm.
Then clearly it takes 2 hours to go
Difference
120
a lot
miles
of
and
time.
1 hour to go, so clearly it takes longer. It takes
Yeah.
longer to go a longer distance if you are stuck with one speed.
Hmm.
And you can wrestle with that separately from these triangles where you can just say, okay, yeah, if I fix the speed, then if I want to go a farther distance, I have to take more time because I don't have any, it all ultimately hinges on the general relationship that in general, distance equals velocity times time. That's really all we're using. And so there's no other way to, if I fix if I fix V and I want this to get bigger, my only other option is to spend more time, which we all
Yeah.
have intuition about. If I it it takes longer to fly, flying can only go 500 miles an hour or whatever in a passenger
Hmm.
airplane. So if you want to fly farther, it'll take you longer.
Hmm.
So once you have that embedded in your intuition, then you're ready for the fact that, well, these different reference frames now, what they're accomplishing is they're making in the two reference frames, the distances are different,
Hmm.
which is no problem unless you're also stuck with a fixed speed. And that's where that
Hmm.
other premise comes into play, right? If you're assuming that there's a shared fixed speed that has to be the same from everybody's point of view to not be biased with respect to one observer, right? That's the whole history about the ether and stuff is like, well, maybe that only is true in one special observer's reference frame, but no,
Right.
it's
It's all.
true in general. So right, it's so fascinating that right, once you conceptually agree on what speed means and you agree on what these distances look like in the two reference frames, then not only is it not strange, but it's like necessary that, well, of course, it's got to take more time.
Hmm.
But somehow we thought we knew what I think the thing is we just without even questioning it, we had in mind that time is some absolute thing that
Hmm.
goes in the background, and this just shows, well, actually, it can't be
I guess like just because of our experience of not going
that fast, right? Right. I guess
that
that's true.
fast, like it just seems like everyone's time is the same.
Right. But when it was something, okay, this came out of my meditation on all this. I didn't need all this as background, but
Uh-huh.
this is something you probably can appreciate. That I literally, for all the, gosh, I started teaching this when I was in college. So, you know, 30, 40 years I've been teaching this. And it never
Uh-huh.
occurred to me before, because I never thought about it at this quite this intuitive level before, which is that um, let me see, I have to phrase this carefully. If trying to really look at what actually happens on a kind of a experiential intuitive level when I say that I think I should be able to make something go faster and faster, essentially what I mean is in a fixed interval of time, I think I should be able to somehow push it so that the amount of distance that's covered grows
Hmm.
arbitrarily large, right?
Hmm.
Mean, that's kind of what my intuition, because speed is distance over time. I
hmm
I'm sort of assuming that there's like a fixed amount of time, and I'm
hmm
just trying to do something that will make the distance that it covers grow, like push by accelerating it or whatever, right?
Yeah.
A- And so what's interesting, and so then in sort of the upbringing of learning about relativity, then I've kind of ingrained it in my mind as, oh, well, you can't go arbitrarily fast. There's a maximum speed limit. But what's interesting is that you can, okay, yeah, let me set it up really specifically. So let's say you are doing you're setting up the events for me that are going to be my
hmm
anchor. So in fact, let's just make it in one spot. So you snap your fingers once, and then 1 second later, you snap your fingers again. And I'm going to use those two events as my reference mark, right? For how I'm gonna be adjusting things.
hmm
I can, in fact, even given the restrictions of relativity, what struck me the other day is that I actually can make my rocket ship move in such a way that those two events that you just did, let's say they're a second apart and zero
hmm
distance apart for you,
hmm
I can I can move in such a way as to make those two events that are x equals zero for you. I can make x prime in my frame. I can make that arbitrarily large. Like I can keep moving faster and faster and faster so that becomes arbitrarily large. What I can't do, what happens though, and that's the part that feels perfect. Like, oh, you say, great, I can move as fast as I
Right.
want then, right? Because the time was
hmm
1 second. We're good. But
hmm
what happens is that in me making the changes in my reference frame to make it so that the distance between those two events that are co, that are x
Simultaneous.
equals zero for you. What's the
I don't
word for
know.
that? Not simultaneous, but
Uh, I know what you're talking about.
yeah, I don't know if is there a word for it in space? It's like simultaneous, but for space. Co-located,
The
maybe.
same. Yeah, that would make sense. The same.
Um, yeah. So those events that are co-located for you, I can make them separated by an arbitrarily big distance for me.
hmm
But what happens is, like if you think back to relativity, where the interval has to stay the same as seen, so that
hmm
it's sort of like the difference between the
Variable.
amount of time and the amount of space has to stay fixed between events that's the invariant thing. So
hmm
what happens is that as I try to go faster and faster, I can make the spacing as large as I want, but the time interval between them grows in my reference frame too, and so that
hmm
x over t stays under the speed of light. Did that work? Did that make sense?
Yeah.
So
Yeah, like because of the ratio.
because the ratio has to stay the same. So somehow, I don't know,
hmm
it felt liberating for me to realize that if I want to, I can make those two events as far apart as I want to. I'm not restricted from doing that. It's just that when I do that, my time will also change
hmm
so that that's why the speed stays confined to be less
hmm
than the speed
hmm
of light is because that's the part I hadn't bargained for. I was just intuitively assuming that I could keep the time interval the same, and in fact I can't.
Right.
But I can make the distance grow as big as I want.
hmm
I don't know, I just thought that was weird.
I love that. I love the power of ratios.
Yes, yes.
I don't know. I feel like the more like physics I do, especially, the more powerful ratios are. Like
Uh-huh.
this instance of ratios, but I mean also with like air resistance and stuff, when we were determining which form of air resistance is more prominent than the other. And like
Okay.
if the ratio is like a whole number, then the um part of air resistance that is in the numerator overpowers the part of the air resistance that's in the denominator. Or like it was like what was it? Um, Forgot.
This is in
Like
classical? Or-
yeah, it was like there's like two kinds of air resistance. One of them is more dependent, is like dependent on velocity.
And one's V squared.
I think so, yeah. Quadratic
Yeah, yeah,
and
yeah. The quadratic one,
yeah,
which is V squared. Right, right, right.
and linear.
Yes, yes. Yeah,
I think I do. I was
you
gonna
can do
say I
so
think
much
I do have
quality.
to leave unfortunately soon, but
That's right.
I think I have like 5 minutes.
Um, so anyway, so yeah, I'm hoping that this is sort of the kind of thing where, like you can delve into deep. I guess that was the theme is
Mm-hmm.
you can meditate on physics ideas in a
Mm-hmm.
way that focuses on the joy of bringing out the insights and not
Mm-hmm.
on necessarily, you can later go back and do hard math if you want to to
Yeah,
to
right.
fill in the details, but you can hopefully do it kind of in a space where you don't have the pressure on yourself to like feel judged about what you know or don't know. You're mostly
Yeah,
lost in the phenomenon, like trying to understand how can this be.
that's a really
Um,
good point.
um, it's kind of what I was
Yeah, no, because
thinking.
I've been noticing too, like even like with like my days off like from work, right? Like I like go to the cafe and then I eat lunch and then I go to the gym and then I probably have like some like meeting or something like in the
Hmm.
evening and then that's like I don't know, like even if the meeting is like, oh, I'm gonna call my friend who lives in Germany and we're gonna speak in German together.
Hmm.
Like it's or like I'm gonna go over to Kata's house. Like it's like and like going to the cafe and going to the gym, like none of these are so like serious and like they're for me to like feel
Play.
good and nice and play, but like it's just I don't know why it's just becoming like so serious. And I feel like in meditating on conceptual ideas, it's not like I don't like I'm somehow making it very serious, which I think is why I'm convinced that it takes up a lot of energy to do
Hmm.
because I have some form of expectation. Like I don't
Yeah.
even know what expectations that I'm trying to meet, but like the expectation that this I have such a tall order of expectations that I'm trying to meet when I meditate that it becomes too much and I don't want to do it.
Yeah.
But like really like I could think about general relativity so incorrectly just to like play around with it. Like I could just say, oh, what if the
Yeah.
speed of light isn't constant, but it like what if the speed limit isn't constant, but like maybe time is constant. Like it could just be it could be whatever I want it to. Like it doesn't like I don't know, I just have
Yes,
some
yes, yes, yes.
preconceived need for it to be correct, which I think that preconceived need for it to be correct is the thing that's making like it's such a tall order and seemingly so energy draining
Yes. It's like playing
when it's
chess
really
where
not.
you want to make the right move, right? As
Hmm.
opposed to
Hmm.
just exploring all the cool things that can happen when, yeah.
Hmm.
Okay, so what about this then for this, next time that you have to think about this?
Hmm.
Like, what if you try to, at the risk of it being an assignment, which makes it maybe not feel like play anymore, but right,
There's no
what?
tall order of
Yeah, I
expectation.
know, but it'll be good practice, right? So what if you
Hmm.
try to? So I'm writing it out. What if you try to find a question about the universe
Hmm.
that, I mean, I'll make it this simple, that feels joyful to explore?
Hmm.
Right? So part of the process is to notice your own like that's your only guiding principle is does this
Hmm.
feel joyful to explore? And then the course correct right? Like course correct if not.
Hmm.
Not on the basis of whether it's right or not, or whether or not you think it's what
Hmm.
you should be. You do plenty of that. So you can give
Yeah.
yourself some freedom to like, for these neural pathways, like you were talking about with your therapist,
Hmm.
right? Like
Hmm.
just to learn what would it feel like to even know, to even have that as a template, right? Like,
Hmm.
so, like start thinking about something like maybe it's black holes, or maybe it's this, what if the speed of light weren't constant or something, whatever you want.
Hmm.
Just pick something,
Hmm.
start going in that direction, and then notice when does it stop feeling joyful? Like, is there a place where
Right.
something comes in and says, oh, that's not right? Or you
Hmm.
should be doing this faster, or you're not
Hmm.
smart enough,
Hmm.
or you're whatever, right?
Hmm.
Whatever
Any
the
kind of crow
voices, the
talk.
crow tries to tell you, right? So whatever it is, but your goal is not to try to answer it or anything. It's to learn about where you get stuck, or to learn
Hmm.
about where, not even where you get stuck, learn about where it stops feeling joyful,
Hmm.
so that you can
And like
see
why
what would
it's
it,
so spiritual.
does that make sense? Like to see
Yeah.
what it would feel like. So just, you know, try to work on something where your goal is to maintain the connection to, wow, this is cool stuff about the universe that I get to explore. And all kinds
Hmm.
of voices will come in and try to make it not fun anymore.
Hmm.
But rather than letting those voices direct what happens,
Hmm.
let them be course correction to say, okay, where do I need to go differently with this thought so that it stays? It's like you're following a path of least resistance to sort of see,
Yeah.
I'm out
Yeah.
running, and when do I feel not safe or something, and I'm going to keep
Hmm.
changing my trajectory until I always feel safe, something like that. And just,
Yeah. That's
you know,
cool.
no goal of, nothing you have to calculate, nothing you have to figure out for a paper, nothing you have to be
Hmm.
prepared for. It's just, and then when we meet next, just tell me about what you thought about, like explain what you thought about and see what that
Are
feels like.
you? I think that
Does that
sounds
sound good?
wonderful.
Okay.
Yeah. And I think, are you potentially available on Saturday?
Yeah, I think so. For a little bit anyway. I have an art exhibit by one of the art professors, Tyler, to go to on Saturday. But yeah,
Oh,
we
that's
can we
cool.
can find a time, I think. I don't remember what time that is, but
Because after I work from 7 a.m. to 12 p.m. your time.
okay.
So after 12 p.m.
Yeah, okay.
I'm
Do you
available.
want to just I think the show's not until like 3 or something. You want to just tentatively
Hmm.
say 1 on Saturday?
Yeah.
And then if either of us
Yeah.
needs to change that, we can change it, but we'll just say 1
That's
p.m.
cool.
Saturday. And then you can tell me about what fun thing you explored, because I think that would be
Wonderful.
really good for all of us, for both of us, just
Hmm.
really good training to remember that we have so many things that come in and try to judge us about, like,
Hmm.
was that a smart thing you figured out, or is it new, or
Hmm.
will people
Hmm.
believe it or whatever? And there's use for some of that, right? To have filters, but I think we need the neural pathways that let us be creative. There's different modes, right? You can do the totally creative mode, and then at some point you put in the skeptic and the critic
Hmm.
that comes in to check it. But you don't want the critic there all the time, or you never get anything off the ground.
Yeah. I think maybe if I think about it as like, like this meditation session
Hmm.
is just a cartoon episode.
Hmm.
Like anything can happen
Yes.
in this cartoon episode.
Yeah.
And then after meditating in the cartoon episode, be like, is it possible to put this cartoon episode and apply it to
Hmm.
the other rules and constraints that we have
Right.
in reality.
Exactly. Yeah, yeah, yeah.
I think that's fun. Okay, cool.
All right.
Sounds great.
Okay. Well, I'm excited to see what the cartoon what
What the
cartoon
cartoon ends up
yeah,
being.
what the
I'll
cartoon
make
is
an
gonna be.
actual
I
cartoon.
was gonna say you could make little cartoon frames. That would be fun.
Yeah,
Yeah.
little storyboard.
Huh.
All right.
All right, cool.
Well,
You
I'll
said
see you on Saturday.
all right, I'll see you on Saturday.
Thank you
All
so
right.
much.
Yeah, have a good rest of the week. I'll see you later.
You too.
Okay.
Bye.
Bye, Logan. Not letting me shut down.